Hello everyone, welcome to this talk. My name is Canqi Yao, a PhD student from the Department of Mechanical Energy Engineering of Southern University of Science and Technology. Today I'm very happy to introduce my work, Incentive-Aware Electrical Vehicle Routing Problem, which is a collaboration with Professor Shibo Chen, Professor Mauro Salazar, and Professor Zaiyue Yang. The motivations for starting the incentive-aware electrical vehicle routing program come from the continuously increasing number of transportation demands and the careers, which is the electrical vehicles. However, with the fixed pickup and delivery times of customers, the performance of the freight transportation is strongly limited within a small operational region. In order to improve the fleet efficiency and to minimize the costs of operation, the fleet operator use monetary incentives to buy the time flexibility from the customers, which can also benefit the customers with the saving of the delivery fee. Here in the figure below, we show you how to model the interaction between the fleet operator and the customers. In fact, there are lots of researchers working on the electrical vehicle routing problem. However, these papers do not consider the interaction between the customers and the fleet operator, which is quite important for the customers to per. Besides, there are also some works focusing on the incentive mechanism design for the mobility on demand system. However, they all do not consider the routing and charging problem jointly. They only focus on a single part. So in order to bridge the research gap, we firstly propose a mathematical model to capture the interaction between the fleet operator and the customers, and then to relieve the computation burden from the bi-level optimizing model. A mathematical reformulating approach is devised consisting of the KKT optimality conditions and the strong duality of the convex optimization problems. Here we first show you the optimization model of the fleet operator. The objective function consists of 5 parts: charging cost plus service revenue plus travel time plus charging time plus discount cost. For consistency, we denote all decision variables by XO. Here you can see the mathematical reformulation of the objective function of the fleet operator. And the constraints have 5 different kinds of constraints. The first one, we use 1A to denote the vehicle flow, which is quite common in the vehicle routing problem. And then the 1B stands for the customer served constraint, and the time windows of all customers are characterized by 1C. The visiting time of all customers is denoted by 1D, and the last constraint 1E represents the dynamics of the state of charge of the battery of the electrical vehicles. Then I will show you the optimization problem of the customer. Here, the customer wants to minimize the inconvenience so-called from the time flexibility while maximizing the discount cost from the fleet operator. Here, in order to quantify the inconvenience, we use a piecewise affine function to characterize the inconvenience occurred from the time flexibility. However, in order to handle the non-smooth objective function, a auxiliary variable in J is introduced, then we can accurately convert customer model into the customer model revisited, which is a convex optimization model, which is quite helpful for the following algorithm design. Then with the optimization model of the finite operator and the customer, we formalize the joint problem of the finite operator and the customer, which is a bi-level optimization problem. Mathematically speaking, it is practical to directly solve the bi-level optimization problem because of the inherent NP-hardness of the bi-level structure and the continuous and the nonlinear and the computation burden for these nonlinear terms. Then, in order to relieve the computation burden, we devise a mathematical reformulation approach, which consists of the KKT optimality conditions and the strong duality of convex optimization problem. Then, in order to handle the non-convex bi-level model, the KKT optimality conditions of the convex Carter model, and the big gamma linearization method are leveraged to replace the Carter model with its optimality conditions. The selection condition is denoted by 4A, and the complementary conditions say is denoted by 4B. However, there are still some nonlinear terms in the opposite function. First, in order to handle the product of two continuous variables, we use the strong duality of the cost model. And then we can linearize these nonlinear terms. Then, in order to handle the resulting binary terms, the big gamma linearization method also applies here with the introduction of a large enough constant m and three continuous variable in eta I, eta 2, and eta 3. With these mathematical reformulation techniques, we finally can obtain the single level mixed integer linear programming, which is much simpler than the previous bi-level optimization model, and which also can be efficiently solved by the commercial solver like Groovy or Diplex in the simulation. In order to validate the superiority of the proposed mathematical model, we solved the resulting single level optimization problem with GroovyPy, which is a Python interface of Groovy. And we compared the numerical results with different gamma 2 and delta bar. Here, gamma 2 means the time sensitivity of different customers, and the delta bar means the upper bound of time flexibility. In the right finger, we can see the operation cost decrease as the size of problem increase because the finite operator can reduce its operation cost by serving more customers. Besides, as the decrease of gamma 2, the finite operator can also achieve a smaller operation cost because the finite operator can pay less money or incentives for the customers with the smaller gamma 2. In the right finger, we show you the diurnal phase saving with different value of gamma 2. Here, when the value of gamma 2 is increased, more diurnal phase of customers is saved because the finite operator needs to pay more for the customers with a larger gamma 2. Then we also test the performance of the proposed mathematical model with different delta bar, which is the upper bound of the time flexibility. As we can see from these two fingers, a better performance is achieved for both the finite operator and the customers, as the increase of delta bar as for the finite operator, they can make a better schedule, routing and charging schedule with a larger delta bar, and the customers can save more delivery fee with a larger delta bar in the meantime. To summarize our work, we propose a bi-level optimization model to characterize interaction between the fleet operator and customers. And to simplify the proposed mathematical model, we devise a linearization approach consisting of the KKT optimality conditions and the strong duality of convex optimization problems. In simulation, we showcase that the proposed mathematical model can reduce the cost of fleet operator by up to 5% and save over to 30% of the total interface for customers. In the future, our work can be extended in the following 3 directions. Firstly, it would be much interesting if we can include the time of use charging price in our model, which is a critical feature, I think, in the modern power system. Besides, we also want to implement the proposed mathematical model in real time with the model predictive control method or rolling horizon method. Thirdly, it will be much complicated if we can consider more complex customer models. Okay, that's all. Thanks for your listening.